back. In this lecture, we will see numerical problems of Norton's theorem. In the last lecture, we have seen the statement of Norton's theorem, the explanation regarding that, and also we have seen a simple problem on Norton's theorem. In the current lecture, we will discuss more problems on Norton's theorem, and I hope that you will be able to determine the Norton's equivalent of a given circuit. Moving ahead, as we have seen in the last lecture, that any network, any complex network, is to be replaced by a current source in parallel with a resistance. We call this current source as Norton's current, and this one as a Norton's resistance. And there are 5 steps which we have discussed in the last lecture. The first thing is you remove the element where we are supposed to determine the response. Number 2, you determine the short circuit current, or what we call it as Norton's current. Step number 3, you replace all the independent sources with their internal resistance. Step number 4, you determine RTH, we also call it as Norton's resistance. And finally, you draw the Norton's equivalent circuit. 5 steps. Step number 1, remove the resistance. Step number 2, determine IN. Step number 3, replace the sources. Step number 4, determine RTH. And finally, draw the Norton's equivalent. Now, let's try to apply these 5 steps in order to determine the Norton's equivalent of the given circuit. See, the question says that using Norton's theorem, calculate the current in the 5 ohms resistor. This is the 5 ohms resistor. Calculate the current in the 5 ohms resistor, which is shown in the figure given below. So, if this is the question which is asked for us, let us try to follow the 5 steps which we have learnt in the previous lecture. So, step number 1 is you remove the element across A and B and mark the terminals across that. So, this is the resistance which is to be removed, right? So, I will mark these terminals as A and B. So, my new circuit is this is A, this is B, and this is 6 ohms, and this is 4 ohms. Okay, so these are the terminals A and B. Now you need to determine the Norton's equivalent between the terminals A and B. So what is step 2? Step 2 is about determining the short circuit current. For that one, I have short circuited these AB terminals. IN can be obtained by shorting A and B terminals. So I have shorted this A terminal and B terminal. Whatever the current which flows through this shorted circuit, that is going to be your IN. So this is shorted here. So this is shorted here. So now you can apply any of the nodal analysis or mesh analysis here. See, I need current in this one. This is going to be my IN. So I'll take this as 0. This is 0. This I'll take it as V1. If you want, you can take it as 0. But try to remember one thing. If this is short circuited and if the current is flowing in this way, then since it is short circuited, no current will be flowing in this one. Anything across a short circuit is basically null and void. So since it is across a short circuit, I am just omitting this thing. Okay, I am just only considering this particular circuit. If that is the case, I do have only one voltage source, one effective node, and here it is going to be my V. So that's why I have written here. Nodal analysis can be applied. It can be observed that there is only one source on the left of network. On the right side, set of 6 and 4 ohms resistor. These are 6 and 4 ohms resistor. They are across a short circuit through which Norton's current is to be. Hence, they can be neglected because it is null and void. Across a short circuit, it is not going to work. So, if my circuit now, it gets limited to, this is 8 ohms, this is 2 ohms, and this is short circuited and nothing else. This is my IN, this is my 5 ohms, this is my 8 ohms, this is my 10 amperes. So if I take this 0, this is going to be my V. So how many paths I do have? This is one path. There is already current here, minus 10, incoming current. This is V minus 0 by 8. This is V minus, again this is 0 by 5. Sorry, this is V minus 2 ohms, right? This is V minus 0 by 2. Okay. So in this case, if I solve this one, the LCM is 8 and I will be getting V is equal to 16 volts. So if I get V is equal to 16, what is the current flowing in this path? 16 minus this point is at 0. This point is at 0. So what is the current here? 16 minus 0 by 2. 16 by 2, it is going to be 8 amperes. So the current through this path is 8 amperes. So that's why IN is equal to 8. Now coming to third step. What I should do, I should replace the entire sources. Already this is open circuit, right? Already this is A, this is B. I am just redrawing the circuit without the sources. This is current source, so I am just open circuiting it. I am not drawing it anything. Okay, this is open circuit. And here again I do have 6 ohms and also 4 ohms. So how does it look like? The current from here, A terminal must go this path or this path, which means that these two are in series, same current is flowing. These two are also in series, same current is flowing. So if these two are in series, what is the resistance? R1 plus R2, it is 10. Here it is again 10. Now both 10 ohms resistor and a 10 ohms resistor. Right side we had 10 ohms resistor, left side also we had 10 ohms resistor. So if the current starts from here, it will take two paths, either this path or this path, which means that both are in parallel. So R1 R2 by R1 plus R2, what are we getting? 5 ohms. Got it. So now what is the equivalent circuit? My equivalent circuit is IN is equal to 8 amperes. This is RN or RTH. This is 5 ohms. So this is my equivalent circuit. I have current source in parallel with a resistance, Thevenin's resistance or Norton's resistance. Now what is the load resistance which I have removed here? It was RL, it was 5 ohms. This one we have removed here. So if you replace this one here, and if you want to determine the current in this one, see, this is a current to be divided into parallel circuits. I1 is to I2 is equal to R1 is to R. Both are of 5 ohms. So equal division will be there, which means 8 amperes will be divided into 4 amperes and 4 amperes. So the current through the load resistance is 4 amperes, and the voltage across load resistance is, this is 4 amperes is flowing, 4 5 are 20 volts will be appearing across the load. Okay, so I hope that now you are able to determine the Norton's equivalent of a given circuit. Try to solve this problem at home. If you carefully see, you need to determine the Norton's equivalent circuit for this one. Okay, and also determine the load current and also load voltage. Okay, we'll solve more problems in the class, and I'll meet you again tomorrow.